on differential equations. So this section is about how to solve a system of first order, first derivative, constant coefficient, linear equations. And if we do it right, it turns directly into linear algebra. The key idea is the solutions to constant coefficient linear equations are exponential. So if you look for an exponential, then all you have to find is what's up there in the exponent and what multiplies the exponential, and that's the linear algebra. So, and the result, one thing we will find, it's completely parallel to powers of a matrix. So the last lecture was about how would you compute a to the k, or a to the 100. How do you compute high powers of a matrix? Now, it's not powers anymore, but it's exponentials. That's the natural thing for differential equation. Okay, but can I begin with an example? And I'll just go through the mechanics. How would I solve the two differential equations? So I'm going to make it, I'll have a 2 by 2 matrix, and the coefficients are -1, 2, 1, -2, and I better give you some initial condition. So suppose it starts u at time 0. This is u1, u2. Suppose everything is in u1 at time 0. So at the start, it's all in u1. But what happens as time goes on, du2 dt will be positive because of that u1 term. So flow will move into the u2 component, and it will go out of the u1 component. So we'll just follow that movement as time goes forward by looking at the eigenvalues and eigenvectors of that matrix. That's the first job. Before you do anything else, find the matrix and its eigenvalues and eigenvectors. So let me do that. Okay, so here's our matrix. Maybe you can tell me right away what are the eigenvalues and eigenvalues anyway, and then we can check. But can you spot any of the eigenvalues of that matrix? We're looking for 2 eigenvalues. Do you see, I mean, if I just wrote that matrix down, what do you notice about it? It's singular, right? That's a singular matrix. That tells me right away that one of the eigenvalues is lambda equals 0. That's a singular matrix. The second column is -2 times the first column. The determinant is 0. It's singular, so 0 is an eigenvalue, and the other eigenvalue will be from the trace. I look at the trace. The sum down the diagonal is -3. That has to agree with the sum of the eigenvalues, so that second eigenvalue better be -3. I could, of course, compute, why don't I over here, compute the determinant of a minus lambda I, the determinant of this -1 minus lambda 2, 1, -2 minus lambda matrix. But we know what's coming. When I do that multiplication, I get a lambda squared. I get a 2 lambda and a 1 lambda. That's a 3 lambda. And then now I'm going to get the determinant, which is 2 minus 2, which is 0. So there's my characteristic polynomial, this determinant. And of course, I factor that into lambda times lambda plus 3. And I get the 2 eigenvalues that we saw coming. What else do I need? The eigenvectors. So before I even think about the differential equation or how to solve it, let me find the eigenvectors for this matrix. Okay, so take lambda equals 0. So that's the first eigenvalue. Lambda 1 equals 0. And the second eigenvalue will be lambda 2 equals -3. By the way, I already know something important about this the eigenvalues are telling me something. You'll see how it comes out, but let me point to these numbers are, this eigenvalue, a negative eigenvalue, is going to disappear. There's going to be an e to the minus 3t in the answer. That e to the minus 3t as time goes on is going to be very, very small. The other part of the answer will involve an e to the 0t. But e to the 0t is 1, and that's a constant. So I'm expecting that this solution will have two parts, an e to the 0t part and an e to the minus 3t part. And as time goes on, the second part will disappear, and the first part will be a steady state. It won't move. It will be, at the end of, as t approaches infinity, this part disappears, and this is the e to the 0t part is what I get. And I'm very interested in these steady states. So that's, I get a steady state when I have a 0 eigenvalue. Okay, what about those eigenvectors? So what's the eigenvector that goes with eigenvalue 0? Okay, the matrix is singular as it is. The eigenvector is the guy in the null space. So what vector is in the null space of that matrix? Let's see. I guess I probably give the free variable the value 1, and I realize that if I want to get 0, I need a 2 up here. Okay? So AX1 is 0x1. AX1 is 0x1. Fine. Okay. What about the other eigenvalue? Lambda 2 is minus 3. Okay. How do I get the other eigenvalue then? For the moment, can I mentally do it? I subtract minus 3 along the diagonal, which means I add 3. I'll just do it with an erase for the moment. So I'm going to add 3 to the diagonal. So this minus 1 will become a 2. And I'll make it in big loopy letters. And when I add 3 to this guy, the minus 2 becomes, well, I can't make 1 very loopy, but how's that? Okay. Now that's a minus 3i, a plus 3i, sorry. That's a plus 3i. It's supposed to be singular, right? If I did it right, this matrix should be singular, and the x2, the eigenvector, should be in its null space. Okay, what do I get for the null space of this? Maybe minus 1, 1, or 1 minus 1. Doesn't matter. Those are both perfectly good, right? That's in the null space of this. Now because a times that vector is 3 times that vector. AX2 is minus 3x2. Good. Okay, can I get a again so we see that correctly? That was a minus 1 and that was a minus 2. Good. Okay. That's the first job. Eigenvalues and eigenvectors. And already the eigenvalues are telling me the most important information about the answer. But now, what is the answer? The answer is the solution will be u of t. Okay, now I use those eigenvalues and eigenvectors. The solution is there are 2 eigenvalues. So there are going to be 2 special solutions here. 2 pure exponential solutions. The first one is going to be e to the lambda 1t x1. And so that solves the equation. And so does this one. They both are solutions to the differential equation. That's the general solution. The general solution is a combination of that pure exponential solution and that pure exponential solution. Can I just see that those guys do solve the equation? So let me just check on this one, for example. Check. I want to check that my equation, let's remember the equation du dt is au. I plug in e to the lambda 1t x1, and let's just see that the equation's okay. I believe this is a solution to that equation. So just plug it in. On the left-hand side, I take the time derivative. So the left-hand side will be lambda 1 e to the lambda 1 t x1, right? The time derivative, this is the term that depends on time. It's just ordinary exponential. Its derivative brings down a lambda 1. On the other side of the equation, it's a times this thing, a times e to the lambda 1 t x1. And does that check out? Do we have equality there? Yes, because e to the lambda 1 t appears on both sides, and the other one is ax1 equal lambda 1 x1, check. So we've come to the first point to remember. These pure solutions, those pure solutions are those pure exponentials are the differential equations analog of last time we had pure powers. Last time, so last time the analog was lambda 1 to the case power x1, some amount of that, plus some amount of lambda 2 to the case power x2. That was our formula from last time. I put it up just so your eye compares those two formulas. Powers of lambda in the difference equation. This was for the equation uk plus 1 equals a uk. That was for the finite stepping by 1. And we got powers. Now this is the one we're interested in, the exponentials. So that's the solution. What are C1 and C2? Then we're through. What are C1 and C2? Well, of course, we know these actual things. Let me come back to this. C1 is, we haven't figured out yet, but e to the lambda 1 t, the lambda 1 is 0. So that's just a 1 times x1, which is 2, 1. So it's C1 times this 1 that's not moving, times the vector, the eigenvector 2, 1, and C2 times, what's e to the lambda 2t? Lambda 2 is minus 3. So this is the term that has the minus 3t, and its eigenvector is this 1 minus 1. So this vector solves the equation, and any multiple of it. This vector solves the equation if it's got that factor e to the minus 3t. We've got the answer except for C1 and C2. So everything I've done is immediate as soon as you know the eigenvalues and eigenvectors. So how do we get C1 and C2? That has to come from the initial condition. So now I use u of 0 is given as 1, 0. So this is the initial condition that will find C1 and C2. So let me do that on the board underneath. At t equals 0 then, I get C1 times this guy plus C2, and now I'm at time 0. So that's a 1, and this is a 1 minus 1. And that's supposed to agree with u of 0, 1, 0. Okay. That should be 2 equations. That should give me C1 and C2, and then I'm through. So what are C1 and C2? Let's see. I guess we could actually spot them by eye, or we could solve 2 equations in 2 unknowns. Let's see. If these were both 1s, so I'm just adding, then I would get 3, 0. So what's the solution then? If C1 and C2 are both 1s, I get 3, 0. So I want like 1/3 of that, because I want to get 1, 0. So I think it's C1 equals 1/3, C2 equals 1/3. So finally, I have the answer. let me keep it in this board here. Finally, the answer is 1/3 of this plus 1/3 of this. Do you see what's actually happening with this flow? This flow started out at, the solution started out at 1, 0. Started at 1, 0. Then as time went on, people moved, essentially. Some fraction of this 1 moved here. And in the limit, there's the limit. As t goes to infinity, as t gets very large, this disappears, and this is the steady state. So the steady state is, we could call it u at infinity, is 1/3 of 2 and 1. It's 2/3, 1/3. So that's we really, I mean, you're getting like total insight into the behavior of the solution, what the differential equation does. Of course, we wouldn't always have a steady state. Sometimes we would approach 0. Sometimes we would blow up. Can we straighten out those cases? The eigenvalues should tell us. So when do we get, so let me ask first, when do we get stability? That's u of t going to 0. When would the solution go to 0 no matter what the initial condition is? Negative eigenvalues, right. Negative eigenvalues. But now I have to ask you for one more step. Suppose the eigenvalues are complex numbers, because we know they could be. Then we want stability. We need all these e to the lambda t's all going to 0, and somehow that asks us to have lambda negative. But suppose lambda is a complex number, then what's the test? What if lambda is a complex number like, suppose lambda is negative plus an imaginary part. Say lambda is -3 plus 6i. What happens then? Could we just like do a case here? If this lambda is -3 plus 6i t, how big is that number? Does this imaginary part play a role here or not? Well, how big is it? What's the absolute value of that quantity? It's just e to the -3t, right? Because this other part, the magnitude, this e to the 6i t, that has absolute value 1. Right? That's just this cosine of 6t plus I sine of 6t. And the absolute value squared will be cos squared plus sine squared will be 1. This complex number is running around the unit circle. It's the real part that matters. This is what I'm trying to do. Real part of lambda has to be negative. If lambda is a complex number, it's the real part, the -3, that either makes us go to 0 or doesn't, or blows up. The imaginary part will just like oscillate between the two components. Okay, so that's stability. And what about a steady state? When would we have a steady state always in the same direction? So I'll take this part away. So that was like checking that it's the real part that we care about. Now we have a steady state when lambda 1 is 0 and the other eigenvalues have what? So I'm looking like that example is like perfect. For a steady state, we have a 0 eigenvalue, and the other eigenvalues, we want those to disappear. So the other eigenvalues have real part negative. And we blow up for sure. We blow up if any real part of lambda is positive. So if I reverse the sign of the matrix A, suppose instead of the matrix I had, the A that I had, I changed it, I changed all its signs. What would that do to the eigenvalues and eigenvectors? If I know the eigenvalues and eigenvectors of A, tell me about minus A. What happens to the eigenvalues? For minus A, they'll all change sign. So I'll have blow up. This, instead of the e to the minus 3t, if I change that to minus, if I change the signs in that matrix, I would change the trace to plus 3. I would have an e to the plus 3t, and I would have blow up. Of course, the 0 eigenvalue would stay at 0, but the other guy is taking off if I reversed all the signs. Okay, so this is the stability picture. And for a 2 by 2 matrix, we can actually pin down even more closely what that means. Can I do that? Let me do that. I want to, for a 2 by 2 matrix, I can tell whether the real part of the eigenvalues is negative. Well, let me tell you what I have in mind for that. So 2 by 2 stability, this is just a little comment. 2 by 2 stability. So my matrix now is just A, B, C, D, and I'm looking for the real parts of both eigenvalues to be negative. Okay. How can I tell from looking at the matrix, without computing its eigenvalues, whether the 2 eigenvalues are negative, or at least their real parts are negative? What would that tell me about the trace? So the trace, that's this A plus D. What can you tell me about the trace? In the case of a 2 by 2 stable matrix, that means the eigenvalues are negative, or at least the real parts of those eigenvalues are negative. Then when I look at the matrix and find its trace, what do I know about that? It's negative, right? This is the sum of this equals lambda 1 plus lambda 2, so it's negative. The 2 eigenvalues, by the way, will have, if they're complex, will have plus 6i and minus 6i. The complex parts will be conjugates of each other and disappear when we add, and the trace will be negative. Okay, the trace has to be negative. Is that enough? Is a negative trace enough to make the matrix stable? Shouldn't be enough, right? Can you make, what's a matrix that has a negative trace, but still it's not stable? So it has a blow up, it still has a blow up factor and a decay one. So what would be so just to see, maybe I just put that here. Now I'm looking for an example where the trace could be negative, but still blow up. Of course. Yeah, let's just take one. Oh, look, let me make it minus 2, 0, 0, 1. Okay. There's a case where that matrix has negative trace. I know its eigenvalues, of course. They're minus 2 and 1, and it blows up. It's got a plus 1 eigenvalue here. So there will be an e to the plus t in the solution, and it'll blow up if it has any second component at all. I need another condition. And it's a condition on the determinant. And what's that condition? If I know that the 2 eigenvalues, suppose I know they're negative, both negative. What does that tell me about the determinant? Let me ask again. If I know both the eigenvalues are negative, then I know the trace is negative, but the determinant is positive. Because it's the product of the 2 eigenvalues. So this determinant is lambda 1 times lambda 2. This is lambda 1 times lambda 2. And if they're both negative, the product is positive. So positive determinant, negative trace. I can easily track down this condition also for if there's an imaginary part hanging around. Okay, so that's like a small but quite useful, because 2 by 2 is always important, comment on stability. Okay, so let's just look at the picture again. Okay, the main part of my lecture, the one thing you want to be able to like just do automatically is this step of solving the system. Find the eigenvalues, find the eigenvectors, find the coefficients. And notice, what's the matrix in this linear system here? I can't help, if I have equations like that, that's my equations column at a time. What's the matrix form of that equation? So this system of equations is some matrix multiplying C1, C2 to give U of 0, 1, 0. What's the matrix? Well, it's obviously 2, 1, 1 minus 1, but we have a name, or at least a letter, actually a name for that matrix. What matrix are we dealing with here in this step of finding the C's? Its letter is S. It's the eigenvector matrix. Of course, these are the eigenvectors. They're in the columns of our matrix. So this is SC equals U of 0. Is that step where you find the actual coefficients. You find out how much of each pure exponential is in the solution. By getting it right at the start, then it stays right forever. You're seeing this picture that each pure exponential goes on its own way once you start it from U of 0. So you start it by figuring out how much each one is present in U of 0, and then off they go. Okay, so that's a system of 2 equations in 2 unknowns, coupled. The matrix sort of couples U1 and U2, and the eigenvalues and eigenvectors uncouple it, diagonalize it. Actually, okay, now can I think in terms of S and lambda? So I want to write the solution down again in terms of S and lambda. Okay, I'll do that on this far board. Okay. So I'm coming back to our equation du dt equals AU. Now, this matrix A couples them. The whole point of eigenvectors is to uncouple. So one way to see that is introduce set U equal A, not A, it's S, the eigenvector matrix that uncouples. So I'm taking this equation as I'm given, coupled with A is probably full of non-zeros, but by uncoupling it, I mean I'm diagonalizing it. If I can get a diagonal matrix, I'm in. Okay, so I plug that in. This is A SV, and this is S dV dt. S is a constant. This is the eigenvector matrix. This is the eigenvector matrix. Okay, now I'm going to bring S inverse over here. And what have I got? That combination S inverse AS is lambda, the diagonal matrix. That's the point. If I'm using the eigenvectors as my basis, then my system of equations is just diagonal. There's no coupling anymore. dv1 dt is lambda 1 v1. So let's just write that down. dv1 dt is lambda 1 v1, and so on for all n of the equations. It's a system of equations, but they're not connected. So they're easy to solve, and why don't I just write down the solution? V is now some e to the lambda 1 t, okay. I guess my idea here now is to use the natural notation. V of t is e to the lambda t v of 0. And u of t will be s e to the lambda t s inverse u of 0. This is the formula I'm headed for. This matrix, S e to the lambda t s inverse, that's my exponential. That's my e to the at. Is this S e to the lambda t s inverse. So my job really now is to explain what's going on with this matrix up in the exponential. What does that mean? What does it mean to say e to a matrix? This ought to be easier because this is e to a diagonal matrix, but still it's a matrix. What do we mean by e to the at? Because really, e to the at is my answer here. My answer to this equation is this u of t. This is my e to the at u of 0. So it's my job is really now to say what does that mean? What's the exponential of a matrix, and why is that formula correct? Okay, so I'll put that on the board underneath. What's the exponential of a matrix? Let me come back here. So I'm talking about matrix exponentials. E to the at. Okay. How are we going to define the exponential of something? The trick, the idea is, the thing to go back to is exponential. There's a power series for exponentials. That's how the good way to define e to the x is the power series 1 plus x plus 1/2 x squared, 1/6 x cubed, and we'll do it now when we have a matrix. So the 1 becomes the identity, the x is at, the x squared is at squared, and I divide by 2. The cube, the x cube, is at cubed over 6. And what's the general term in here? At to the nth power divided by, and it goes on. But what do I divide by? So you see the pattern. Here I divided by 1. Here I divided by 1, by 2, by 6. Those are the factorials. It's n factorial. That was like the one beautiful Taylor series. The one beautiful Taylor series, well, there are two beautiful Taylor series in this world. The Taylor series for e to the x is the sum with x to the nth over n factorial. And all I'm doing is doing the same thing for matrices. The other beautiful Taylor series is just the sum of x to the nth, not divided by n factorial. Do you know what function that one is? So if I take, this is the series, all these sums are going from 0 to infinity. What function have I got? This is like a side comment. This is 1 plus x squared plus x cubed plus x to the fourth not divided by anything. What's that function? 1 plus x squared plus x cubed plus x fourth forever is 1 over 1 minus x. It's the geometric series, the nicest power series of all. So actually, of course, there would be a similar thing here. If I wanted, I minus AT inverse would be, now I've got matrices. I've got to have matrices everywhere, but it's just like that series with, and just like this one without the divisions. It's I plus AT plus AT squared plus AT cubed and forever. So that's actually a reasonable way to find the inverse of a matrix. If I chop it off, well, it's reasonable if t is small. If t is a small number, then t squared is extremely small, t cubed is even smaller. So approximately that inverse is I plus AT. I can keep more terms if I like. Do you see what I'm doing? I'm just saying we can do the same thing for matrices that we do for ordinary functions. And the good thing about the exponential series, so in a way this series is better than this one. Why? Because this one always converges. I'm dividing by these bigger and bigger numbers. So whatever matrix A and however large T is, that series, these terms go to 0. The series adds up to a finite sum. E to the AT is completely defined. Whereas the second guy could fail, right? If AT is big, somehow if AT has an eigenvalue larger than 1, then when I square it, it'll have that eigenvalue squared. When I cube it, the eigenvalue will be cubed. That series will blow up unless the eigenvalues of AT are smaller than 1. So when the eigenvalues of AT are smaller than 1, so I better put that in. All eigenvalues of AT below 1, then that series converges and gives me the inverse. Okay. So this is the guy I'm chiefly interested in, and I wanted to connect it to, oh, okay, how do I get, this is my main thing now to do. How do I get e to the AT? How do I see that e to the AT is the same as this? In other words, I can find e to the AT by finding s and lambda, because now e to the lambda t is easy. Lambda is a diagonal matrix, and we can write down e to the lambda t, and will right in a minute. But how do you see that we're hoping that we can compute e to the AT from s and lambda, and I have to look at that definition and say, okay, how do I get an s and a lambda to come out of that? Okay, do you see how I want to connect that to that from that definition. So let me erase this, the geometric series, which isn't part of the differential equations case and get the s and the lambda into this picture. Oh, okay. Here we go. So identity is fine. Now, all right, you see how am I going to get A replaced by S's and lambdas? Well, I use the fundamental formula of this whole chapter. A is S lambda S inverse and then times T. That's AT. Okay, what's A squared T? I've got the divide by 2. I've got the T squared, and I've got an A squared. All right. So I've got there's A. Now square it. So what happens when I square it? We've seen that before. When I square it, I get S lambda squared S inverse, right? When I square that thing, there's an S and an S cancels out an S inverse. I'm left with the S on the left, the S inverse on the right, and lambda squared in the middle, and so on. The next one will be S lambda cubed S inverse times T cubed over 3 factorial. And now, what do I do now? I want to pull an S out from everything. I want an S out of the whole thing. Oh, look, I better write the identity how. I want to be able to pull an S out and an S inverse out from the other side, so I just write the identity as S times S inverse. So I have an S there and an S inverse from this side, and what have I got in the middle? If I pull out an S and an S inverse, what have I got in the middle? I've got the identity, a lambda T, a lambda squared T squared over 2. I've got e to the lambda T. That's what's in the middle. That's my formula for e to the AT. Oh, now I have to ask you, does this formula always work? This formula always works. Well, except it's an infinite series. But what do I mean by always work? And this one doesn't always work. And I just have to remind you of what assumption is built into this formula that's not built into the original. The assumption that A can be diagonalized. You remember that there are some subset of matrices that don't have n independent eigenvectors, so we don't have an S inverse for those matrices, and the whole diagonalization breaks down. We could still make it triangular, I'll tell you about that, but diagonal we can't do for those particular degenerate matrices that don't have enough independent eigenvectors. But otherwise, this is golden. Okay, so that's the formula, that's the matrix exponential. Now it just remains for me to say what is e to the lambda t. Can I just do that? Let me just put that in the corner here. What is the exponential of a diagonal matrix? Remember, lambda is diagonal, lambda 1 down to lambda n. What's the exponential of that diagonal matrix? Because our whole point is that this ought to be simple. Our whole point is that to take the exponential of a diagonal matrix ought to be completely decoupled. It ought to be diagonal, in other words, and it is. It's just e to the lambda 1t, e to the lambda 2t, e to the lambda nt, all zeros. So if we have a diagonal matrix and I plug it into this exponential formula, everything's diagonal, and the diagonal terms are just the ordinary scalar exponentials e to the lambda 1t. Okay, so that's in a sense, I'm doing here on this board with like formulas what I did on in the first half of the lecture with specific matrix A and specific eigenvalues and eigenvectors. So let me show you the formulas again. But I guess what should you know from this lecture? You should know what this matrix exponential is, and like when does it go to 0? Tell me again now the answer to that. When does e to the at approach get smaller and smaller as t increases? Well, the s and the s inverse aren't moving. It's this one that has to get smaller and smaller, and that one has this simple diagonal form. And it goes to 0 provided every one of these lambdas, I need to have each one of these guys go to 0. So I need every real part of every eigenvalue negative. Right? If the real part is negative, that takes the exponential, that forces the exponential goes to 0. Okay. So that's really the difference. If I can just draw here's a picture of this is the complex plane. Here's the real axis, and here's the imaginary axis. And where do the eigenvalues have to be for stability in differential equations? They have to be over here, in the left half plane. So the left half plane is this plane, real part of lambda less than 0. Where do the eigenvalues have to be for powers of the matrix to go to 0? Powers of the matrix go to 0 if the eigenvalues are in here. So this is the stability region for powers. This is the region absolute value of lambda less than 1. That's the stability for, that tells us that the powers of A go to 0. This tells us that the exponential of A goes to 0. Okay, one final example. Let me just write down how to deal with a final example. Let's see. So my final example will be a single equation, u double prime plus a bu prime plus ku equals 0. One equation, second order. How do I, and maybe I should have used, I prefer to use y here, because that's what you see in differential equations. And I want u to be a vector. So how do I change one second order equation into a 2 by 2 first order system? Just the way I did for Fibonacci. I'll let u be y prime and y. What I'm going to do is I'm going to add an extra equation, y prime equals y prime. So I take this, so using this as the vector unknown, now my equation is u prime. My first order system is u prime. That'll be y double prime y prime, the derivative of u. Okay, now the differential equation is telling me that y double prime is, so I'm just looking for, what's this matrix? Y prime y. I'm looking for the matrix A. What's the matrix in case I have a single first order equation and I want to make it into a 2 by 2 system? Okay, simple. The first row of the matrix is given by the equation. So y double prime is minus b y prime minus k y, no problem. And what's the second row of the matrix? Then we're done. The second row of the matrix I want just to be the trivial equation y prime equals y prime, so I need a 1 and a 0 there. So matrices like these, the general case, if I had a 5 by 5, if I had a fifth order equation, and I wanted a 5 by 5 matrix, I would see the coefficients of the equation up there, and then my 4 trivial equations would put 1s here. This is the kind of matrix that goes from a fifth order to a 5 by 5 first order. So the eigenvalues will come out in a natural way connected to the differential equation. Okay, that's differential equations. A parallel lecture compared to powers of a matrix, we can now do exponentials. Thanks.